All right, so you're seeing the grades there for all 3 exams you've taken. So each of these numbers down here is a particular student, and they're in order from highest to lowest for exam 3. So the highest grade, we had 200s on the test, and then the lowest was a 60, and we had a lot in between. So let's see, how many A's? We had 1, 4, 5, 6, 7, 8, 8 A's. And then we had almost A's. 1, 2, 3, 4 B's, 1 C, 5 D's, right? Average on this test was an 83.4, which was an improvement from the previous test of 76.6, and right under the first exam average. Standard deviation went up. So we had a very low standard deviation on the first test, and then a very high one on the second test, and it came back down.
Second test is brutal.
Yeah, so the second test, which I think I've told you all, I told you at the beginning of the semester, first test is usually the best, second test is usually a struggle, third test is usually better than the second, and then the final, pretty much the average is like a 30. So, no, I'm kidding. No, the final, though, historically is not that great, and I think it's a combination of a few things. One is that students go in, they play with their grades, and they see what they need, and they realize, oh, I only need a 40 to get a C, and so they shoot for a 40, 41. You know what I mean? I mean, people do that, or they say, you know, B is not possible, or an A is not possible, so they just kind of don't try as much. So I think that kind of skews the grades, and like, so you might think it's a more difficult test when it's actually, like if you look at the grades, you might be like, oh, that's a tough test, but a lot of it is students are just not putting in 100% to it.
That's what I think is right now towards the end.
Yeah.
I know it's early to talk about the final, but remind me, it's not cumulative,
It's almost all chapter 8.
okay. And it's
Yeah.
about the same length as, it's really just.
No, because the final's 2 hours, 45 minutes. Right? So that's the only test that we take that's more than, normally it's 100 minutes, right? So it's going to be, what's that, almost 180? So like, 165? Something like that.
So is it going to be like a really long test?
Well, time-wise, yes. But like number of problems, I don't know. I'd have to go look. Yeah. Yeah, so there it is. You can kind of see some students have gone up, some students have gone down. You know, it is what it is. Any questions on that?
What's the grade line?
The grade is exam 3.
Oh, okay.
Yeah. Back to. So we need to get going. All right, we need to keep cranking along here. So we are in chapter 8, section 2 still. We were talking about telescopic series, telescopic and collapsing series, and I thought maybe I would do one more of these telescopics, and then we're going to move on to the next section. So let's do this one. So the question here is, does this series converge or diverge? Well, on a test, on a final, I would actually ask you to find the sum of it. If it converges and it's telescopic, I'll say find the sum, which gives you a hint that it's telescopic. But for this, let's just act like we know nothing about it. We're asked if this converges or diverges. So the question is, does this converge? Does it diverge? If it converges, then what does it converge to? Right, so does it converge or diverge? If it converges, then what does it converge to? All right, so what if we try the very first test, the nth term test? We're going to do this just mentally. Nth term test, the pregnancy test one, right? Let n go to infinity. We get infinity over infinity. L'Hopital in here would give you a 1, right? And natural log of 1 is 0. And so that would go to 0, which tells you nothing, right? So then you say, okay, is it geometric? Well, what do y'all think? Does this look geometric to you?
No.
Why not?
There's a natural log.
There's a natural log in there, right? And normally for geometric, you have the n up in an exponent, right? So not geometric. What else did we have? Harmonic. Harmonic, you need constant over linear. We have a log. It's not constant over linear, okay? So not harmonic. What else do we have? P-series. Don't we have P-series? Yes? Does that not sound familiar? No? Hold on. Harmonic. Oh, geometric. Oh, P is the next section. I'm sorry. Harmonic. Apologize. Yeah, okay, so no, that's it, right? That's all we had. Geometric, harmonic. So telescopic is the only natural thing left for us to think, right? At this point in the class. So what I'm going to do is let's just start writing out the series, all right? Let's start writing out the terms. If I plug in 1 into this, I get natural log of 4 over 1 plus natural log. Now I plug in 2, I should get 5 over 2 plus natural log of 6 over 3 plus, and if I write it that way, I don't see anything that's canceling out, right? Like there's nothing that goes away. But I can try and rewrite the original series using different notation. Or not different notation, I can use property of logs. So when you have natural log of division, you can turn it into 2 logs with subtraction. So I'm going to turn this into natural log of n plus 3 minus natural log of n. Right, isn't that a property of logs? I'm using this property, natural log of, let's say, x over y is equal to natural log x minus natural log y. This is a college algebra property of logs. We used it when we were condensing or expanding expressions with logs in college algebra. So if I do it that way, and then I start writing out the terms, the first term, when I plug in 1 here and 1 here, I get natural log 4 minus natural log 1, and then add to that natural log 5 minus natural log 2, and then add to that, you all see what I'm doing? Natural log 6 minus natural log 3. And again, initially this doesn't look like anything's really going on, except that we have some subtractions in here now, don't we? And so I think eventually something's going to cancel. Natural log 7 minus natural log 4 plus natural log 8 minus natural log 5. Didn't I have a natural log 5? Oh, I had a natural log 4 too, didn't I? Right there. That natural log 4 actually would get wiped out by that one. Yes?
Was there any giveaway to you to how far out you were going to have to go?
Kind of. The n plus 3 tells me that I'm going to have to go like 3 over before I get to something that's going to cancel. The fact that the n and the n plus 3, those differ by 3, I'm going to need 3 terms before I see it, before I see the cancellation. Y'all see it? So now let me just visualize what's going on. This natural log 4 cancels with, where is it? Right here, that one. And this natural log 5 cancels with that one, right? And so I told y'all when I showed you the example last time, I said I like to verbally state what the cancellation is. So the way I'm going to verbally say this is that the first term, right? The first term cancels with the what? This is in this parentheses, this is the second term, right? With the second term, but how many parentheses down? 3 parentheses down, but 3, how do we want to say this? 3, can I just say 3 down? You know what I mean?
Yeah.
3 down. So the first term here will cancel with the second term there, but we have to be three parentheses downstream for the cancellation to happen. And that's the pattern, right? That's the pattern. You can also state this backwards. You can say that the second term cancels with the first term, right? The second term cancels with the first term, but 3 upstream, right? 3 up. So if you're looking at second terms in a parentheses, you know that it cancels with something the first term, but you have to be 3 upstream instead of 3 downstream. It's just 2 different ways of verbalizing the same cancellation property.
So that's important to identify because when you do the right side.
Yeah, we're gonna have to work backwards. All right, so that's the first thing, right? With the telescopic, the first thing is to see the canceling. All right, see the canceling first. Any questions? Okay, now what I'm going to do once I've established the canceling, I'm going to try and come up with a formula for the sum of the first n terms. So I'm going to now write what S sub n is. It's the sum of the first n of these. So it would be natural log of 4, natural log 4 minus natural log 1 plus natural log 5 minus natural log 2 plus natural log 6 minus natural log 3 plus natural log 7 minus natural log 4. I feel like I'm missing something here. No, 4, 7, 4, 5, 6, 7. I'll do one more. Natural log 8 minus natural log 5, right? I'm just summing, right? I'm summing, and I need to go, I'm going to stop at the nth one. So plus dot, 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 right? Dot, dot, dot. Now I'm going to run out of room on the screen here. So what I'm going to do now is do it down here. So what would that last term be? If I plug n into that. Natural log of n plus 3 minus natural log n. Is it all right if I write it like that? That's the last term. If I stop at n, that's where it would stop.
So as a rule of thumb, you want to leave space.
In front of it, yeah. Now plus, now what's the term in front of that? So for this one, I plugged in n, right? I plugged in n into that formula up there. The one in front of that, I'm plugging in what? Yeah, one less, so n minus 1. So what would happen if I plug n minus 1 into that formula? Well, the one that's split apart. N plus 2, n minus 1. Right, so I'm just basically taking 1 away from each of these. Let me go upstream one more. What would the parentheses above, in front of that one be? Natural log n plus 1 minus natural log what? N minus 2. Ooh, that's bad. N minus 2. How far am I going to have to go upstream?
3 up.
3 up to see the canceling, right? That's why it's important to understand the canceling. They're happening every 3. So I've got 1. Let me see. I need to go 1, 2. It should be on the next one I should see canceling. Let's see. The first one would be natural log of n minus natural log of n minus 3 this time. So as we move from here to here, all I'm doing again is subtracting 1 from each of these each time. Take 1 away there, take 1 away there, take 1 away there, right? And same with this. Do y'all see the canceling? What cancels?
So it's what is it? The first term, second term. So 1, 2, 3. So natural log of n. The ln.
Y'all see them?
The n plus 3 is canceled.
All right, so y'all are seeing them. Some of you are seeing them. Let me start from here. All right, tell me, is this a first term or a second term? First term. What do first terms cancel with? Second one's 3 down. So do I have a second one 3 down? Yeah. So this cancels with that one. Okay. This is a what?
Second term.
This is a second term. Second terms cancel with first terms 3 up. Up. There's no up. There's no upstream from this. Do you see? This stays. Nothing kills that one. Except that natural log 1 is 0. Yes, but just generally speaking. How about this one? It's a first one. It cancels with something down there, right? And there is something down there to cancel with. So that goes away. Now where is it? Oh, we see it. Yeah, it's right there. Okay, this one is a second term. It requires that I have something upstream. I don't. Not 3 upstream. So that stays, right? This is the first one. It cancels with something 3 down. Do we have something 3 down? Where is it? I don't see it.
No, it's there.
It's in there. It's in the dot, dot, dot. It's in this dot, dot, dot. It's actually the next term, isn't it? Or the next piece. So that cancels with something in this dot, dot, dot. Okay? How about this negative or minus natural log of 3? It's a second term. It needs something 3 up. Do we have something 3 up? No. So it stays. All right, this is the first one. It needs something 3 down, second term. Is it in here somewhere?
Yes.
Yeah, it's in there somewhere. Gone. Okay, and now we've gotten here. This one canceled from before. This one cancels down here somewhere in the dot, dot. Right? And now you can see that everything's gone away over here except this, this, and this, right? Those 3 are still there. And now we're going to do the same thing, but let's do it on this piece here at the very end. And I'm going to start at the far end right here and work my way backwards. This is the second one, right? Second ones cancel with first ones 3 up. It's up there. Okay, this is a first one. First ones cancel with second ones 3 down, but we've stopped, haven't we? So this one's not going to go away. It's going to stay. This is a second one. Second ones cancel with first ones 3 up. Where is it? It's in there somewhere, right? Because that dot, dot, dot continues. Dot, dot, dot plus. So this continues, right? Yes?
So is it safe to just say that all the second terms are canceled with something down?
Yeah, this, and this all cancel with something in here. This one. Right? All the second ones are going to be gone, but not all the first ones. Right? The first one there stays because there's nothing downstream. This first one, there's nothing downstream. Stays. This one stays, right? And then the rest of them are all gone. These are all gone. All the dot, dot, dots inside collapsing series. They'll collapse, all falls away, everything goes out. So the only thing you're left with is some stuff at the front, some stuff at the back.
So
Yes.
the unique one there is the, what is it, the first set we had from the right side? Because that one has 2 terms canceled.
Oh, this one is the one that's different. Yeah, once you get here, as you continue moving into the dot, dot, everything's going. Everything's going to go away, right?
Yeah, that's right.
Because the next one, what would the next one have been? It would have been natural log of n minus 1 minus natural log of n minus 4. And see that natural log of n minus 1 that I just put here?
Yeah.
Cancels with
N plus 1.
that one right there.
Oh, okay.
You see?
Yes.
So it would be gone. And then this one cancels with something over here. Right? This is the first one. This is the first one. It cancels with the second one 3 down. 1, 2, 3. Second one. First one cancels with something here. Yeah? Yes?
So, what's the question asking?
Well, we haven't answered the question yet. We've just,
What's the question?
does this converge or diverge? If it converges, what does it converge to?
Oh, the sum?
The sum, the series, the original series. This up here. Yes?
So writing it all out this way, going from left to right and then right to left,
Mhm.
is just so we can see the pattern in what you said?
Yes.
First cancel, okay.
Yeah. Well, when we wrote it out the first time, right, I didn't stop at n, did I? I just wrote it out until I started to see canceling. And then once I saw the canceling, I wrote down what the pattern of canceling that I saw was. And then I wrote it out and I stopped at n and then figured out what canceled. And now what this gives me is a formula for S sub n. What is S sub n? Let's write down what S sub n is. S sub n will be whatever was left at the front, negative natural log 1 minus natural log 2 minus natural log 3, right? That's what's left at the front. These 3, 1, 2, 3. But I still have some stuff at the back. Where's the stuff that was left? This plus natural log of n plus 1 plus this one, natural log of n plus 2 plus the last one here, natural log of n plus 3. Those three are left, aren't they? Everything else has collapsed away. And now to figure out what this series is, to figure out what the sum of this series is, I need to take this formula and do what with it? This is the critical step now.
Take the limit.
Take the limit. See what happens when n goes to infinity of this. So take this limit now. What's the limit as n goes to infinity of this s sub n?
So are you just trying to determine divergence at this point?
Yes, I'm trying to figure out if it converges or diverges. If it converges, this is going to give me a number, and that's going to be what the sum goes to. If it
Oh, that's right, yeah, because you don't actually have to, like, you said, I think you said the series follows the sequence of the sum, or something of that sort.
Exactly. We have a series, we have a sequence, which is this in here, which is just a bunch of numbers, and we're adding them up. So we create a new sequence that shows you the sum of either just the first one, or the first two, or the first three, or the first four, or the first five. We came up with a formula for the sum of the first n. And now what we're going to do is say, well, what happens if we let that go to infinity? That sum becomes infinite, and we're hopefully going to get an answer, but let's see what happens. Negative, natural log of 1 is 0, so that's 0. Minus natural log of 2, natural log of 2 is just some number. Minus natural log of 3, natural log of 3 is just some number. And then where does that go as n goes to infinity? Infinity. Infinity plus infinity plus infinity. What happens? Goes to infinity. What is this going to then? What happens to the series? It diverges.
But the natural log should have a, like, some sort of behavior when it goes to infinity.
It's not asymptotic. It grows. Natural log function looks like this, and it grows.
Oh, yes, that's right.
Yes.
Are series exclusively sums of sequences?
Our series. Well, your series is going to be, you're going to have a formula in here, right? And that formula you could look as a sequence. Yeah.
Well, because like series are sums of sequences, right?
Yes.
So are they only sums of sequences, or could it be like when sequences like multiply with themselves or something like? Is that still?
That should still be a sequence. If you take two sequences and multiply them together, it's still a sequence.
It's not like series is only when you add.
Oh. So, I don't know if I understand your question, but I think I do. Let's take something simple. This means 1 plus 2 plus 3 plus 4. Are you asking me, can we have 1 times 2 times 3 times 4?
Yeah, like is that like a series?
Is that what you're asking me? Instead of doing 1 plus, can we do 1 times? Yes. That is, and the notation changes. We don't use capital sigma. We use capital pi.
That's what that means?
Capital pi means pi for product, s for sum. And then you go n equals 1 to infinity of n. And what that means is 1 times 2 times 3 times 4 times 5 forever. This means 1 plus 2 plus 3 plus 4. So yeah, this is just a different mathematical operation that we don't talk about in this class. Yeah. But it's a useful thing, just not, we don't do it here. Do more math. If you did more math, you would see it, promise. Nope, not in Cal 3. In Cal 18, no. No, actually it's not in the calculus sequence. You won't see it in the calculus sequence. And I'm trying to remember where I saw it the first time, I don't know. I can't tell you. Somewhere. Okay, you got the idea? Telescopic. The danger in telescopic, imagine you did this problem, right? This is what someone's going to do this on the final. We'll see who, someone here is going to volunteer to do this. Someone's going to write this out. They're going to be like, I see the pattern. It's natural log of 4 minus natural log 1 plus natural log 5 minus natural log 2 plus natural log 6 minus natural log 3 plus natural log 7. Oh, shit. Natural log 7 minus natural log 4. One more. Natural log 8 minus natural log 5, right? And they're going to go, okay, there it is. That's what's happening, right? They're going to say, oh, there's cancellation. They're going to be like, this cancels with this, and then they're going to say that cancels with that, and they're like, nothing cancels this, nothing cancels that, this cancels in here, gone, this cancels in here, gone, this cancels in here, gone, this doesn't go away, that's, okay, so everything else goes away. My answer is those three things. Someone's going to put that, and that's going to be their answer on the test, these three things. And they're going to say everything here goes away. And it's completely wrong. Because then you're saying it converges, right? This is 0, this is a number, that's a number. So you're going to say it converges to a number. When it doesn't, it diverges.
So what went wrong there? Was it you canceled on the fourth term 2, right?
What's that?
On the fourth set, you canceled 2 of them? Instead?
No, I didn't do anything wrong. I didn't do anything wrong. What I did is I assumed that cancellation, that you're not getting.
Oh, it's not, you didn't factor the right-hand side, is what you're saying?
That's right.
Okay.
That's right. You're always left. As you keep moving out, you keep on being left with a little term. Just imagine you keep on subtracting. It's going to cancel. It's going to show up. Cancel, show up. The thing that keeps showing up is getting bigger and bigger and bigger. So it's like every time it goes away and then comes back, it's huge. In other series, that collapsing series that converge, what happens is, yes, you have some stuff at the end that keeps on canceling out. It shows up, cancels, shows up, cancels, shows up, cancels. And those are getting smaller and smaller and smaller and smaller. So as they show up and cancel, it's not making a huge difference on these first 3 terms. Where here, the stuff at the end is like getting infinitely big. So it doesn't converge. It's almost like a sign at the end. It's like going up and down, up and down, up and down. It's that the tail end of these, the pieces at the end are not going to 0. Okay, we need to move on. Oh, wait, did I show y'all the alternate notation? I did not. I need to show y'all this. You can add this to your formula sheets. The one that has all the tests on it. You can add it there, although I feel like it's there already. Okay, remember geometric series? A geometric series looked like this. It was A plus AR squared plus AR cubed. One more, AR to the 4th plus ... That was it, right? And we said that we have a condensed notation for this, that's equal to sum n equals 1 to infinity of AR to the n minus 1. That was the way I introduced geometric series to you. And we can verify that this creates this, right? If I let n be 1, 1 minus 1, 0, right? R to the 0 is 1, A times 1 is A. And then I let n be 2. If that's a 2 here, 2 minus 1 is 1. So now you have AR. And you let n be 3, and then it gives you the AR squared, and n be 4, right? There's an alternate notation for this. It's another series like this where we can change it to look slightly different, but it makes the same exact series. It's this. What we can do is change our index, and instead of starting it at 1, we're going to start it at 0, and then go to infinity, and then our formula changes like this. You don't have to have n minus 1 here. You have n. Now, we've never started our index at 0, have we? When we started talking about sequences, chapter 8, section 1, we said a sequence is a function that goes from the natural numbers into the real numbers. So we always started with 1, didn't we? And we've been pretty stringent with that condition of starting at n equals 1. What this is subtly telling you is that actually we can start anywhere we want. We don't have to start at 1. We can start at any starting point as long as they keep going up by 1. All right?
So only geometric does that?
No.
Okay.
All series we can change the index starting point. Yes.
So say if you had n equals -1, you would put -1.
Plus 1. It would become plus 1.
Oh, that's right.
Yeah.
You started at -1.
Yeah. So let me show you something. This is going to be weird first time you see it, all right? This is what we call going from here to here. This is called changing the So what I've done is I have taken, instead of saying n equals 1, I made it n equals 0, right? I've changed the index from 1 to 0. I want you to think about how I actually did that, like what I did. Ready? Watch this. First time you see it, again, it's going to look weird. What I did over here is I took this n equals 1, and what I did is I took it and I replaced this n with n minus 1. No, plus 1, sorry. What I said is, look, I'm going to replace this n with n plus 1. Okay? Just let me replace n with n plus 1 right now. If I do that, replace n with n plus 1, now solve this for n. What would you get if you solved that for n? N equals 0, right? But what did I do? I replaced the n with n plus 1, right? You got to do it here too. Whatever you do here, you got to do here. So what happens if I replace this with n plus 1? What's n plus 1 minus 1? N, and it becomes n. So again, I started with this. And I said, hey everyone, I'm going to take all my n's and replace them with n plus 1s. If I do that, if that becomes an n plus 1, then this becomes 0. And if I replace that with n plus 1, it becomes n plus 1 minus 1, and that becomes just n. I'm going to see if you understand that, because I'm going to give you another one. I'm going to see if you can change the index for me. So using this right here, using that geometric series, what if I wanted you to write the geometric series in a slightly different notation, but I wanted you to start your index at 4? I want the equivalent expression to that, but starting your index at 4, not at 1. So think about, what would you have to do to make this a 4? You'd have to add 3, right? So what do I need to replace this with? N minus 3. Do you all see that? If I replace this with n minus 3, then I would add 3 to both sides, and that would give you the 4. So the conversion I'm going to make here is I'm going to replace all n's with n minus 3. Let's do that. So if I just write this whole thing down again, replace your n's with n minus 3. This becomes what here? N equals 4, which is what I wanted you to do, right? And then a r to the n minus 4. Ooh. We'll get more practice with that. Oh, whoa. It was on just a little to the right. And a little long. Point blank, point blank. We're going to get more practice with this, but I wanted to at least show you. So the new formula you can put on your sheet, all right? The geometric series formula.